Well, let's continue talking about hydrogen bond and have a look on the boundary conditions. Hydrogen bond is interesting in crystal engineering because in the case of hydrogen bond, especially in the case of moderate or the second class of hydrogen bond, we can use directionality. Directionality to build up, to form robust networks is extremely helpful. Yes, this is one point. The second point is talking of boundary condition is that very often I have shown we are not only talking of 1 point hydrogen bond, very often we use 2 points, something like this. And very often we have something like this here, bifurcated hydrogen bond, free-centered interaction. It's very often founded, so multi-forsated interaction. And very strange and sometimes helpful to understand crystal structure is the fact that we are talking in this case of cooperativity, that if you're looking to the aggregated, which is held together by hydrogen bond, when you see that the free hydrogen has higher acidity, what does it mean? Have a look. Looking to alcohol. Well, if you look to dimer, so the first unit, you will find something like this. ROH interacts with the neighboring oxygen, with the hydrogen. Now there's another hydrogen here. That's what I'm meaning. And with hydrogen, that is not interacted this moment in any hydrogen bonds, aggregation has a higher acidity. And what's going on, this means that such hydrogen forms more often a hydrogen bond much more easier than the monomeric form. So dimer forms easier additional hydrogen forms than monomer, trimer easier than dimers, and so on. Yes? So if you have such a systems, you will predict or suggest that we will find another hydrogen bonds forming of, chains. And the experiments show that this change disrupt, and in the case here, if we have 7, 8 or 6 units which are in this change, then you will see some other effects dominate, and when it's not going on this change. But sometimes very nice to see something like this. Well, okay. Talking about different types of hydrogen bond, a nice example is to illustrate the different types of hydrogen bond is carboxylic acid. We have shown this is typical formation of hydrogen bonds of carboxylic acid with dimer. Very nicely, and I have shown you this picture. I've shown you one of the first slides. You can use it to form, 1D, 2D, and 3-dimensional networks. But this was theory. If you look in the Cambridge structure database, then you will see only 33% of all dicarboxylic acid crystallized in such manner. Question: what happens to the rest? 66% do not crystallize from this dimer. Wow, huge amount. Well, what we see is several cases, very often we see the formation of arrays, which are catenaries named, something like this. The change going on. Chains catenary in the card. This is one point. The second possibility is that further accepted groups are around in the environment, and so we have a competition between them. question is always which hydrogen bond is formed. I will show you an example. Looking to 4-hydroxybenzoic acid. Okay. Which hydrogen bond could be formed? First question. And the second question is which hydrogen bond is formed? We have two interesting units here, carboxylic acid on one side and the hydroxy side on the other side. This is a crystal structure. We see is here the dimer is formed and the linear arrays of hydroxy chains are formed. Nice example is to show that in this case the functional group there's no competition between the functional group. Yes, on one side there's dimer, on the other side the hydroxyl group. In this case we are talking of insolation of a functional group. In the other case, I will show you pyridine carboxylic acid and in free position, nicotinamide. Yes, carboxylic group here, and this is the nitrogen group here in the backbone. Well, if you now look in the structure database, then you will see that mostly 90% you will see the interaction forming hydrogen bond of a carboxylic group with the nitrogen here. On only 10% of the compounds you will see with dimer unit of a carboxylic acid. So in this case there is a competition between the two functional groups. Well, next point could be why this dimer function is not observed, but solvents are present in the crystal structure, mostly hydrates. Very nice example. If you look, this is a snapshot of a crystal packing of oxalic acid. So we have linear chains of this unit going on. In the presence of water, what we see is there's no interaction between two oxalic acid. What we see is that the oxalic acid is linked by two water molecules. Yes. So the water oxalic acid or the acid water interaction is preferred in contrast to the oxalic acid or the acid acid interaction. So based on your experience and based on the Cambridge structure database, you can say in requirements that hopefully, yes, you can observe such units are that first of all you have no competition, reduction of competitive functions, and the second is that with the carboxylic group, not carbonyl group, carboxylic group is directly attached to the aromatic backbone. With competition between dimer and catamer is not only restricted to carboxylic acid. For example, glycol analyte, this case here, the same problem. If you look to the crystal structure where two polymorphs known, and what we see is one is the catamer function, thermodynamically more stable polymorph. We'll see it is a keto function, the keto group here interacts with the hydroxy group. Here, keto with the hydroxy group here, forming this catamer. And the second polymorph, you see it here, this is the hydroxy here, with the chain. And the second point is the dimer. And in this case we have the amino group and not the keto function, the hydroxy function. And you see it here. This is the dimer with the catamer. So, for you, go home message, very often you have a competition, and it's if you see where it could be in competition, you must be very carefully, you must show very intensively to the structure, thinking about the environment, thinking about competition, thinking about groups who can disturb or can, I don't know, build multi-centered function and so on and so on. Okay. Next point. Directly link to hierarchies. Competition, when we are going to hierarchies of hydrogen bonds. Well, there's a very, very easy rule that fits very good. The best hydrogen bond is formed by the best hydrogen bond donor and the best hydrogen bond acceptor. This rule fits really good. And the second best hydrogen bond is formed by the second best hydrogen bond donor and the second best hydrogen bond acceptor. Very nicely, very nice. And I will show you an example, isonicotine amide. Yes, what you hear is nitrogen is a pyridine backbone, we have the amide function. Well, we have two here basic sides, the less basic side, two, the nitrogen, and the more basic side here. Well, now, very easy crystallization experiment. You take this isonicotine amide and mix it with two different acids with different strength. Yes, acids with different strength, acidity. Well, what you see is, the result is the nitrogen atom forms hydrogen bond with a stronger acid, and the amide carboxylic O forms second best hydrogen bond with a weaker acid. Sorry, my mistake by myself with a more basic. I think I didn't say it, but you see it here written. Okay? Well, exceptions of this very fitting rule, always very often, I must say, well, it's always the same. It's a question of competition. If you have the number of donors and acceptor doesn't fit, are quite different, one you will see very often multi-centered hydrogen bonds. You can see it, and once again, if it's a competitive groups and the near environment, when also with the rules fits not really good. Steric factors, as last not week. Polymorphic behavior is also a reason. Polymorph we will talk about a little bit later, several slides later, several videos later. We will talk about polymorphism, and we will see polymorphism is a very mystery chapter, and well, only sometimes you need only tiny tools, very tiny tools to switch from one polymorph to the other. And so this directly has an impact on the formation of hydrogen bonds. Okay. And when thermodynamic crystallization takes place, the shown hierarchy may not apply. Well, going on to weak hydrogen bonds. Weak hydrogen bonds, these are hydrogen bonds with reduced electronegative of epsilon or epsilon bar. No? For example, CHO. You remember this example from the crystal Cambridge structure database, was one. Or CHN, that's another very nice example of weak hydrogen bonds. In this case, we have a less directionality, this is very important. And on the other side, such weak hydrogen bonds could have an impact, a dominating impact on crystal structure, mostly if strong hydrogen bonds are not present in crystal structure. In this case, such weak hydrogen bond could have and dominating impact. No? And very important is that attributed to a weakness of a hydrogen bond, a weakness of this intermolecular interaction, the position, the substitution pattern, or general the location of a functional group is very important for the formation of hydrogen bond recognition motives. Yeah? And it depends, as it's written here, on the substitution pattern. On the other side, I will show you, if you have no strong hydrogen bond, and as I said, the importance and a weak hydrogen bond can have an importance, we can sometimes nearly the same, comparable, if we look to the pattern, to the topology, nearly the same like strong hydrogen bonds. For example, I will show you how you can use it. No? For me, looking here to this molecule, it's a pyridine, and with a substituent, a CH triple bond. No? And here in this case is nearly the same. Now the nitrogen is not the same position, or you can say the substitution pattern 1,4 position here, and you can say this is 1,3 position. And in this case you have 2 nitrogen. If you look at the crystal packing, what you see is, in this case, we are easily, for formation here going on with line, formation of this linear chains. If you look here, what we see is a zigzag chain, nitrogen, and here we have a hydrogen of acetylene group. And in this case, we have a zigzag chain once again, and additionally, we have here to the second nitrogen the formation of a hydrogen bond, weak hydrogen bond. Yes? So once again, you have only weak hydrogen bonds, but you see very nicely how weak hydrogen bonds dominate, are responsible for the crystal structure. Another impact, especially if weak hydrogen bonds are present, could be fluorine atoms in the crystal structure, as substituents. Well, have a look here. This is the electronic potential map of benzene. This is the electronic map of monofluorinated benzene. Yes? No, sorry, pentafluorinated benzene. This is the leaving hydrogen. This is the hydrogen which is not substituted. You see with this here, this remaining hydrogen shows an increased positive charge in comparison to benzene. Yes, positive charge, a high acidity. And by involving fluor substituents in this structure, you increase the acidity of the remaining hydrogen, and you can use exactly this hydrogen in crystal engineering. You see it here. Have a look on these 3 compounds. It's very similar to this compounds here, the linear and 1,4 position, 1,3 position, and here with 2 nitrogen. Very similar. Here 1,4 position, and here it's not exactly the same. You see. Have a look. In this case, the nitrogen has changed position. Here, once again, formation of linear chains. In such intermolecular interaction, you will only see if you have an increased acidity of a hydrogen. In the case of here, this position, I would say ortho position, where you see once again this very nicely zigzag change. And In this case, hydrogen has changed its place in the aromatic system when you see the formation of dimers. So, nice example how fluorine substituents can be used in crystal engineering. And it's not restricted in this very spacey compounds. Have a look, for example, here. If you try to crystallize pyridine with isopropanol, 2-propanol, you will not have any success until now. Nobody. The reason is there is a really, this is a pKa value, of isopropanol, and if you now using this perfluorinated 2-propanol, hexafluoropropanol, we will see it has an impact on the pKa value, and in this case it's really possible to get a co-crystal of pyridine with a perfluorinated propanol. So once again, you can use fluor substituents in crystal engineering to increase controlled acidity of desired or hydrogen which could be used in crystal engineering tasks, projects. Well, that's it for the topic hydrogen bond.